Welcome back to the lab. Welcome back to EE for Everyone. Today we're talking about the AB Amplifier project, specifically some awesome comments on our previous video. You asked a lot of great questions, and I want to answer them now for a couple reasons we're going to talk about in a second. As I was editing some of our videos in this series, there's something that was just kind of bothering me, it was eating away at me a little bit, and I really don't think that I did a great job of highlighting the purpose of this series, like the problem I was trying to solve. Specifically, we strive to create pretty finished designs in general, something that you could in theory duplicate at home, use to learn something about electronics, like something that serves a purpose and is generally useful. And as we're stretching our legs in 2021, I'm starting to explore a slight shift in format, and I guess I didn't really communicate that well. Whereas by communicate that well, I mean communicate that at all. Basically, if you look back at our previous videos, you'll notice some long stretches, 6 to 12 months dedicated to a single project. That's awesome, but only if you're interested in that project. If you're more interested in power electronics, you'll be bored if the next 6 months is about microcontrollers. It's a really great thing that our community has been growing, though that comes with an ever harder challenge to make content that everyone on the channel, including myself, is interested in. Basically, a big part of the idea of EE for Everyone, at least for 2021, is to work on more smaller projects, or if we want to work on a larger project, to break that 6 to 18 month project down into bite-sized pieces. Now that will give us some convenient stopping points to throw some fresh content in the loop or grab some different material and throw that in the mix for good measure. This series was never intended to produce the best or even a particularly good Class AB amplifier, but it's meant to serve as more of an example just so that we can talk through some theory and fundamental principles of amplification and some of the trade-offs between the different amplifiers. Like, I wanted to use this as a platform to discuss the make versus buy trade-offs that come with analog circuits, like amplifiers. And that's great, and it's really important to me, but that's also not really the focus of this video. As a part of restructuring our workflow, changing the cadence of projects, rethinking about the way we see EE for Everyone, like there are some seriously exciting shifts coming to EE for Everyone, and there's a lot of great projects that are coming to the channel. Some are big, some are small, and I feel like I've been doing an awful job of keeping up with comments in the meantime. That is, I've been doing a terrible job of responding to comments. Like, months at a time will go by before I respond to any. And I want to make two things very clear. First of all, I read every single comment on our videos. The nice ones, the mean ones, the incredibly insightful ones, the thoughtful ones. I especially love the constructive ones. I read and appreciate every single comment. Thank you. Thank you so much for how you lean in. Thank you for your support, for your encouragement, and for always helping us to make EE for Everyone as good as it can possibly be. Seriously, I can't say it enough. Thank you. You, the community, are the best part of this channel. The second thing is that I've found myself with very little margin lately, very little room in my schedule to just sit down and respond to those wonderful, wonderful comments. They light up my phone, I read these comments, and they linger in my mind for months. I'm thinking about you as a community, and for those that reach out, you individually and specifically. I remember what you say, and it weighs on my mind when I don't reply. Like, I'll find myself feeling anxious that you're somehow waiting on me to reply to this random comment you left on a video. Probably not the healthiest thing, but hey, that's where I'm at, and we're having a conversation. At the end of the day, one thing that I need to accept is that I am absolutely by no definition of the word a full-time YouTuber, and I have been trying to show myself some grace in this area. Like, I'm not going to be able to reply all the time because we're doing a few things over here. I'm going to reply when I can. I'm going to reply to as many comments as I can. Thank you so much for commenting more on our videos than I can reply, and I will continue to read every single comment that you leave. So then, that's a weight off my chest, something I just needed to share. So why did I make this video? What are we? 7 minutes in. Why did I make this video? I made this video because you left a lot of great comments on our last video, and I want to use this video to answer them. Text just didn't work as well. I needed to get some pictures in there. First things first, Power Max. Thank you, sir, for the scholarly comment. Let's go line by line on this one. Current source, we'll talk about that in a moment. Darlington's, heck yes. Let's explore that Darlington comment in LT Splice. By adding that resistor, I expect we'll see a large efficiency gain. I've added a 1 mega ohm resistor where you suggested. We see an efficiency of 47% at this operating point, 13.79 watts out, 28.97 watts in. 47.6% efficiency. Changing that to the suggested 480 ohm value, I'm seeing 13.73 watts out and 28.86 watts in, 47.5% efficiency. Removing that base emitter resistor completely, LT-Spice now shows 13.789 watts out and 28.966 watts in, 47.6% efficiency. So all of these are pretty much the same. I'm not sure if this is an LT-Spice not showing me the real world sort of thing, but I'd expect the current gain to be reasonably realistic, like in the simulation. Either way, the simulation is suggesting that diverting some of that base drive isn't having a big impact just yet. Maybe I'm missing something obvious here, and in case you aren't super familiar with this transistor configuration, let me briefly walk through why this is a fantastic suggestion by PowerMax, and why this was and still is worth investigating. Basically, even just a tiny current through Q5, maybe even microamps, that might be enough to make a few tens of microamps flow through Q1, leaving it partially on when we may prefer it to have it completely off. We may be unintentionally leaving Q1 and Q4 on more often than we want. Adding the suggested base emitter resistor provides an alternative path for the emitter current flowing through Q5 and Q3 around the power transistors. This essentially allows us to introduce a threshold current where enough current needs to be flowing through an alternate path for small currents to flow, meaning that if there's only 10 microamps flowing through the first transistor in the Darlington pair, something to the tune of 99% of that current will go through the resistors we added, rather than through the power transistors Q1 and Q4. Of course, when we actually drive Q3 and Q5 hard, all of the aforementioned transistors will turn on as expected. Great suggestion, PowerMax. I'm not sure exactly why the simulation didn't allow us to demonstrate the principle as well as I had hoped, but it is a great suggestion nonetheless. On to the next point. And I'm not even going to try to pronounce that, but yes, I've seen that before. Instead of using the Darlington configuration, you can see how the intrinsic diode, specifically the one between base and emitter, are not placed one after the other cascaded like with the Darlington. Rather, you see the collector emitter voltage plus a forward bias diode, so somewhere around a volt of drop rather than the approximately 1.4 volts for the Darlington pair. I mean, that sounds great and all, but I know how to pronounce Darlington, and Silky. No. Nope. Say that 5 times fast. Okay, this last point is great, but leaves a lot to unpack. Op-amp instead of common emitter amplifier, and it seems like you're suggesting a class B, so that means there's no steady state current for increased efficiency in this configuration. That design would lean on, as you mentioned, PowerMax, seriously, this is an amazingly well thought out comment, which is why I needed to share this. There are so many great little design details hidden in here, but this design would lean on the slew rate of the op-amp to get it through crossover. Make sure you get subscribed so you don't miss where we play around with this little board, whatever, I'll throw some B-roll on there. We used a simple 3904, 3906 pair of output transistors to increase the output current capability of a standard op-amp and compared that to a different one. Wait until you see how little crossover distortion we observed on this board. It's quite frankly awesome. So that's a fair point and a valid comment. Our little buffer board was made with the intention of driving capacitive loads, but there's absolutely nothing stopping a person from using a higher power transistor for a circuit like this amplifier to turn a humble commodity op-amp into a pretty decent power amplifier with fixed gain and good linearity. So about that Class D part, heck yes. I know Class D is a big point of contention in the audio amplifier community, and I am all about performance. That's all I've got to say. I don't mind if there is or is not switching involved in my amplifiers, so long as none of the high frequency energy gets into my headphones or speakers. It makes no difference to me how the sound is made. I know that ruffles some feathers out there, so let's just move on. Thank you again, PowerMax, for the great suggestions. As we move on, I'll make one last attempt to mash all of your suggestions together into an awful simulation. And yeah, nice. This thing is a hot mess, and I love it. The simulation barely runs. In fact, I had to run this like 4 times to get it to be stable enough to give me a few whatever, which is how you know it's an awesome simulation. I just grabbed a random op-amp. I've never used an OP77 before, at least not to my knowledge, but I figured it'd be pretty op-ampy. Anyways, to throw this in there, the efficiency came out to about 55% with 17.6 watts out, 31.5 watts in, so yeah, it has pretty good performance, and I love it. Anyways, I burned an hour or so playing around at LT-Spice, so I think it's time to move on to our next comment. Thank you once again, PowerMax. This is not the first time you've dropped a glorious comment on our videos. I appreciate you. As for the rest of you, hopefully this gives you a couple more things to think about if you're considering making your own analog amplifier. This brings us to our second comment. This is a great question, and it points back perfectly to our overview of Class A, B, and AB amplifiers. Like Luciano said, AB amplifiers are a blend of the two types, and the real efficiency depends on how well it's optimized or how far it's pushed towards the A or B side, how much current is flowing through that totem pole in the default state. The most interesting thing to me is that we just saw 45% efficiency in the simulations we did today, which is pretty bizarre because we just said 35. So thank you, Mohammed and Luciano, for that wonderful comment. Now I want to blend that one with the next one to talk about something, and we'll revisit this whole deal a couple videos down the road. This comment is from Eric, and it raises a great question. I must admit, I know something that you don't. I've actually finished recording the series, and the editors are working hard to get it ready for you, so I've already built and tested this circuit in hardware. As a small spoiler, one of the things we noticed is that the temperature compensation, where I mean using diodes instead of pure resistors, didn't work very well. As the main power transistors got hot, the forward voltage dropped, causing them to pass even more current, and eventually they just ran away. If I wouldn't have noticed the current increasing rapidly and shut down the system, I'm very sure that I would have damaged these transistors, these parts. So in theory, yes, using the same transistors as a diode pair would more closely match the performance of the parts in question, but only if the transistors are the same temperature. That seems easy on the surface, but even if we tied all 4 transistors to the same heatsink, one transistor would have a hot die, the one's actually dissipating the power, the heat source heating the heatsink, and the other one would need to be colder than the heatsink. Now that could be a 30 to 50 degrees Celsius temperature difference if we're actually pushing the amplifier. And that's not really that close to the same temperature. That's not great. That's a very tricky problem to solve with discrete components. So I guess in theory, absolutely yes, that would help. But in practice, part-to-part variance and temperature differences will always exist if you're using discrete parts. And so now this leads us to something critical that we need to highlight about off-the-shelf Class AB power amplifier modules. They have one advantage that I don't have and will never have while limited to standard discrete components. Let's use the SSM 2019 as an example of a Class AB amplifier circuit. Even if we used matched transistor pairs made on the same die, that still wouldn't be as good as if every single transistor was made at the same time with the same process and was designed such that those silicon structures are all as close to identical as practically possible. Just look at this block diagram. 5 current sources, multiple matched pairs, diodes, all of these silicon devices packed as close together as possible and manufactured at the same time. Now, is it possible to build an equivalent circuit out of discrete parts? Of course it is. But just imagine how complex our PCB would become. Building an identical structure out of discrete semiconductor devices would be impractical at best, and quite frankly, that's why I chose to keep this project simple. That's why we built an imperfect Class AB amplifier, because even if I don't like it, the art form of building awesome analog amplifiers out of discrete components is a dying art if it's not already dead. That design challenge is quickly being transformed into an academic thing or an integrated circuit design challenge, where managing cost and thermal performance becomes critical. After all, it's possible to find AB amplifier modules on DigiKey, which are rated to deliver 2 channels of audio power with more than 100 watts per channel, and that chip costs around $10. It is actually difficult to find a complementary power amplifier transistor pair that will even come close to that price. Remember, that's 2 channels. So that means for everything, you're trying to design down to like $2 a part? If you're spending all your money on those 4 transistors? Yeah. So a discrete amplifier will likely cost more, take longer to design, and perhaps not even work as well as its integrated counterpart. That's worthy of a big yikes from me. Once again, thank you all for being a part of this lovely community. Thank you for your time and attention, and thank you for these comments. I think this conversation is very important because without this video, the Amplifier series would be missing a lot of great information and a lot of great color. If we only talk about what we built, never slowing down to talk about why we built it and how we thought about it, that is not best for anyone. So I hope that you enjoyed hearing more about why we built a design that we knew wouldn't be the best in this Class AB amplifier, and please let me know your thoughts in the comments below. I really do love hearing from you. I want to give a special thanks to our channel members. I really appreciate the extra step you've taken to support us directly. Well, if you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we'll be continuing this discussion by discussing the schematic and layout for this amplifier. I can't wait! Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thank you for staying till the end. Bye! Oh, one more thing. For those that stayed after, I know this is a little corny, but I just gotta say, I mean, normally I like tape it to my face. I didn't have the audacity to do that for this video, but I do really like the way this sounds because the mic really close to my face and I'm not in a treated room, so there's tons of echo in here. And compared to what it sounded like, don't get me wrong, this microphone is better, but this one is so close to my face, like, let me know what you think. We've been using these for a lot of stuff, and yeah, I don't know, whatever. Can you get over the appearance? Is this okay? Can you get over this? I don't know, whatever. I got no shame. It's fine. It's dorky. I'm okay with it. Anyways, let me know what you think. I think it's fine.